Thank you everyone for joining us this afternoon for this webinar on exceptional floods, insights into their frequency and changes from 3 simulation approaches. As Bastien said, I'm Manuela Brunner and I'm an assistant professor both at ETH Zurich and the Snow and Avalanche Research Institute in Davos, where I'm leading the hydrology and climate impacts group in mountain regions. You might all remember pictures like the one you see on the screen. This picture was taken 2 years ago in the Ahr Valley, and it shows the devastating impacts of the flood event that hit Germany in July 2021. After such highly impactful flood events, we usually ask ourselves, how frequently do these types of events occur, and how might their frequency change as we move into the future? In order to answer questions related to the frequency of such extreme events, we have to perform some sort of frequency analysis. Such a frequency analysis usually starts with a stream flow record, ideally at a daily scale, ideally also spanning a period of 30 years or longer. And from this record, we then initially just extract a flood sample by defining floods either as annual maxima or as indicated here using a peak over threshold approach. We can then use this sample of flood events to fit a flood frequency curve. And that fitting of a flood frequency curve consists of fitting a distribution to our data sample that relates discharge on the y-axis to the frequency of events on the x-axis, and this frequency is often used as a substitute for the return period that tells us something about the mean recurrence interval of extreme events in time. Once we have fitted such a flood frequency curve, we can use it to answer 2 different types of questions. The first type of question starts with an observed event, for example, this 2021 flood event in Germany, and we can, based on the measurement that was taken for that event, use the flood frequency curve and determine the corresponding non-exceedance frequency or also the return period. So we can use that curve to answer questions related to how often do events such as the one we have observed in the past actually occur. But we can also turn this around and ask, how big is a flood with a specific return period? For example, a return period of 100 years. That's the type of event that happens on average every 100 years. Now, the problem with these types of frequency analysis based on observations is that we cannot really grab what's happening in this upper right corner of the distribution, where the most extreme and the most impactful events are actually happening. So there we have very limited information, and the shape of this curve is actually rather uncertain. So what can we do about this? What can we do to fill this knowledge gap about these very severe and impactful events? We can indeed use different types of large ensemble approaches to increase the sample size and to fill this gap about what's happening in the upper tail of the flood frequency curve. And these types of ensemble approaches, they can be of different nature. They can include stochastic approaches. They can include approaches where we couple a weather generator with a hydrological model. They can also include approaches where we stochastically simulate stream flow directly, or they can involve different types of model change where we use large climate ensemble and feed them through a hydrological model. Now, today in this talk, I would like to introduce or talk about 3 different of such large ensemble approaches, and I would like to start by talking about stochastic simulations. In the second part of my talk, we will then look into reanalysis ensemble pooling, and towards the end of the talk, we're going to look into single model initialized large ensembles, such called SMILES. And for those of you who've attended Clara Desert's talk last week, this last part eventually links to what she's been talking about during her talk. I want to apply these three simulation approaches to three different applications. So first, we want to use the stochastic simulation to look at spatial floods in the United States. We then use the reanalysis ensemble pooling to study extreme floods in Europe. And last, we use these SMILES to study the relationship between increases in extreme precipitation and increases in flooding. Let's jump right in by this stochastic simulation. And here, I really want to generate a large ensemble of spatially comprehensive flood events in order to study spatial floods over the United States. Why am I interested in spatial flooding? So spatial floods, as opposed to just regional floods, they might or are probably even more impactful because they challenge water management in the sense that resources have to be distributed in space, and emergency management has to take into account that resources are not just allocated in one location, but they're actually needed in multiple places at the same time. In this first part of the talk, I would like to answer the question of how probable are widespread flood events in large river basins. And when I talk about large river basins, I'm here referring to these 18 river basins in the United States. And for each of these river basins, I have a set of observations which I can use to calibrate and tune the stochastic model. The stochastic model starts with daily streamflow observations from all these gauges. And the goal here is really to fit a model that can not just represent the distribution of streamflow, but also the spatiotemporal relationships of flows at different locations in space. This is important because we're interested in regional as compared to just local floods. So we use these observations, and we first fit a 4-parameter kappa distribution to our observations in order to model the distribution of daily streamflow values at the individual locations. Then we turn to modeling the spatiotemporal dependencies, and we do this by decomposing this time domain signal into the frequency space by using the wavelet transform. In this frequency domain, your time series is now represented by a time series of amplitudes and by a time series of phases. Now we want to add some stochasticity and randomize the process in order to generate new yet unobserved time series. And we do that by simulating just one single time series of white noise. We take this white noise and we also use the wavelet transform on it to derive a set of randomly generated phases. And these phases are now used to introduce the spatial dependencies about sites. And we do that by replacing the observed phases by these randomly simulated phases, combining them with our observed amplitudes, and just using the inverse wavelet transform to get back from the frequency domain to the time domain. Now, this signal already shows the spatial temporal dependencies in flow among different sites, but we don't yet extrapolate to yet unobserved streamflow values. In order to do this extrapolation step, we now use our fitted kappa distribution, and we just transform our simulated flows to the kappa distribution using the parameter estimated in step 1. And what we end up with is now a spatially consistent set of streamflow time series that has been simulated for different locations in space. Now let's look at an example and see how this model actually performs. I'm here showing you observed streamflow time series for 4 different catchments in the United States, just labeled station 1 to station 4. And for the same stations, I've simulated 3 years of data using this stochastic model. What you see is that while obviously the values change a bit and also the temporal pattern changes a bit, these spatial patterns or the relationships between the different locations actually seem to be maintained. And we trust the model in the sense that it can represent not just the distribution of flow, but also the spatial dependencies in flow at different locations. So we apply this model to all the catchments in our data set now. And from the simulated daily time series, we extract flood events using a peak over threshold approach, as illustrated at the very beginning of my talk. And what you see here now is just simulated regional flood events that have been simulated over the domain of the United States. So essentially, the black dots just pop up whenever a station or a catchment shows flooding, and the dot remains white in case no flood event is simulated. And you see that we simulate different types of flood events, which are sometimes spatially coherent. Sometimes they also affect different locations in the United States a bit more randomly, but most of the time there's some spatial consistency in it. Now we use this large ensemble of stochastic time series to answer our initial question of how susceptible are large river basins in the United States to widespread flooding. We do that by extracting peak over threshold flood events for each of the catchments from the simulated series. And then we put together a binary occurrence matrix indicating for each catchment which event it was actually affected by. Using that matrix, we then perform a regional frequency analysis that quantifies the probability that within a certain region, 70% of the catchments are actually jointly flooded. In order to compute this probability of regional flooding, we take two perspectives. On the one hand, we look at these 18 different river basins over the United States. And on the other hand, we also take a more local perspective and quantify these probabilities for a region that is domained by a radius around the station of interest. Today, I'm just going to actually show you results from the river basin perspective. When you now look at the probability of regional flooding, so at the probability that 70% of the catchments that are within one of these regions is jointly flooded, you see that there's some regional patterns emerging. You see that the probability for regional flooding is, for example, rather high or comparably high in the eastern part of the United States. It's also comparably high in the western part of the United States and in the south, but it's comparably low in the Columbia River Basin and the upper part of the Missouri, and also in Florida. Now, these floods, they obviously don't all happen in the same season. So we now take a seasonal perspective on regional flooding, and we see that overall the probability for regional floods is highest in spring, followed by winter and summer, and regional floods are very unlikely in the fall season. And then for each of these seasons, we already again see some patterns emerging. We see in winter that regional floods are most common in the east and in the west. Similar picture in the spring. And then in summer, we just see some regions that are actually prone to regional flooding, while most other regions are very unlikely to be affected by regional floods. So we've used this observation-based stochastic model to look into the probability of regional flooding, which are rather rare phenomena that are hardly present in the observations. And this is why we use the stochastic model to shed more light on this question of how the probability of regional flooding varies in space. Now let's turn to a different type of approach that could also be used to increase the sample size and study these rather extreme or exceptional flood events. And here I want to introduce this idea of reanalysis ensemble pooling that relies on a reanalysis ensemble. And we're going to use this approach to study the frequency of extreme floods in Europe And here I'm moving back to a local perspective and actually looking at local floods in Europe, but we're going to focus on very high return periods. That's again very rare flood events that are hardly part of the observations, or we only have very few of these events in our observational records. So the question I want to answer here is, how big is the 200-year flood in the different catchments in Europe? You see displayed on this map, and we're going to later focus on 4 example regions, one in France, one in Central Europe, or 2 in Central Europe, and then 1 in Northern Europe. Now let me introduce this idea of the Reforecast ensemble pooling, which we again use to increase sample size. So we use the Reforecast or streamflow Reforecast from the European Flood Awareness System, EFAS, and this simulation chain consists of a hydrological model. In the case of EFAS, that's the least flood model. And this least flood model is fed by predictions from a numerical weather prediction model generated by ECMWF. And it's just actually one model, but the model is combined with different initial conditions. And that just means that the initial conditions are perturbed in 10 different ways, such that we can increase the sample size by a factor of 10. In addition, that weather prediction model is run for different lead times. So it predicts stream flow for tomorrow, the week after tomorrow, and the stream flow in a month. And we can also use the predictions of these different lead times to actually increase sample size. So we have different lead times ranging between 0 hours and 46 days. And we just, to not overdo it, only choose every 48-hour time step. And then we have these 10 initial perturbations, which both help us to increase sample size by a factor of 240. That's 24 lead times and 10 different perturbations. So now we have these 240 time series, and for each of these time series, we can again extract flood events as a basis for our flood frequency analysis, which helps us to substantially increase our sample size. The only problem we face with that is that the different lead times are actually not totally independent. And this is what you see illustrated here for 4 different catchments, A to D. And for each of these catchments, you have indicated the correlation of runs that are run for different lead times from 0 hours to 24 days on the right. And what you see in most catchments, there's a decrease of this correlation as you increase the lead time. So the further you look into the future, the more independent get your model runs. While for some catchments, you at some point approach 0 correlation, which is what you would like to have, because you're interested in model runs that are actually as independent as possible, and you want to include those that just replicate information that's already contained in another model run. So what you don't want to see is actually this example A, where you see that correlation remains at a very high level, even when you go to very long lead times. What you prefer is examples such as number B, where you go down to 0 already at very early lead times. So we need to find a sweet spot between removing a little bit of information that's just duplicated for the shorter lead times and retaining the novel information for the longer lead times. And this cutoff threshold might vary slightly for each catchment, but we want to identify some common sense. So just to show you a bit more about this, where this correlation issue is actually an issue, it's mostly observed in the high elevation catchments where floods happen in summer and are driven by snowmelt. So there's a lot of memory in the system because floods are, among other processes, triggered by snowmelt. And that's where we retain quite a good predictability also for longer lead times, while we have these more low elevation regions where we observe more precipitation driven winter floods, where predictability is not so low and the correlation between different lead times is much lower. So clear relationship between the elevation of a catchment, with high elevation catchments being those that have more correlation and more dependent model runs. So we now want to find some sweet spot, remove the duplicate information, and actually retain the novel information we gain from using these reforecast runs. So what we decided to do is to cut the ensemble at a lead time of 22 days. So what we do is we remove everything on the left. We remove all the information generated for very short lead times, because we're assuming that this is actually duplicate information, and we retain those model runs which we consider to be more or less independent, and that's the remaining 13 lead times from 22 days out to 48 days. And then we also still have our 10 perturbations for the initial conditions, which leaves us still with 130 event sets, which we can use to increase our sample size by a factor of 130. So we now take the floods observed for all these 130 time series, and we pool them into just one pot. And using this entire large sample, we then again perform a frequency analysis that establishes a relationship between the magnitude of flows and the frequency or return period of flows. I've here illustrated such flood frequency curve for 4 different catchments. And let me just guide you through that plot. We see in gray the bootstrapped estimates from our observations. Then in gray, we see the confidence interval of our flood frequency curve that was derived from our observations. So basically, in most of the cases, just roughly 30 flood observations. And then in orange, you see the flood frequency curve, which we derive from our re-ensemble pooled data. So the sample that is 130 times larger than our observation sample. And what you see is that the confidence interval of our simulated values is much smaller than the one of the observations, which means that by increasing the sample size and by using these re-ensemble forecasts, we're much better able to constrain the uncertainty of our flood frequency curve. This is maybe even more pronounced for the second catchment, Oosterach, where the confidence interval of the observations is huge, and we managed to narrow down the confidence interval quite a bit by using the re-ensemble pooling sample. Now let's use this new approach based on the re-ensemble forecast pooling to estimate the magnitude of different flood events from return periods of 10 years, 20 years, 50 years, 100 years, and 200 years. What we see is that independent of the return period, the largest flood events are estimated for the alpine regions, where we are at higher elevations, and the further down we go, the lower are actually the estimated flood peaks corresponding to the 50-year return period, but also to the 200-year return period. We try to relate these estimated flood magnitudes of the different return periods to different catchment attributes. Green colors indicate positive relationships between flood magnitude and the catchment attribute. Red colors indicate negative relationships. And we see that the steeper the slope of a catchment, the higher is the specific estimated flow, the higher the precipitation, the higher is the estimated flow. And then we also have some alleviating effects on flood magnitudes, such as through dam regulation. So this is a second approach you could use to estimate the frequency of very extreme floods, this re-ensemble pooling approach, which relies on some sort of a re-ensemble, which you could generate yourself, but also use existing re-ensembles that are around. Now, in the last part of my talk, I would like to use a single model initialized large condition ensemble to study the relationship between increases in extreme precipitation and extreme flooding. What is the background here? So in the past, I've had several conversations with colleagues from the climate community who were like, yeah, floods should actually increase because of increases in extreme precipitation. And then as a hydrologist, I also always caution them a bit and say, well, yeah, but if we look at the observations, we don't actually see such a clear signal with respect to how floods have changed in the past. There's regions where we see increases in flooding. When we look at the past 40 years, there's regions where we see decreases in flooding over the last 40 years. But when we look at the change signal in space, we don't see such clear patterns usually. And this is because, as hydrologists, we know the land surface matters too. And it's not just about increases in precipitation, it's also about changes in snowmelt contributions, changes in soil drying, or changes in evapotranspiration. So what we wanted to do here is to shed a bit more light on the relationship between precipitation increases and flooding, and in particular, we wanted to see whether there's a certain point or threshold above which actually precipitation increase start to translate into flood increases, just because the soil moisture is high anyway, and there starts to be a more direct coupling between precipitation and stream flow. This is also a question you can not really address by just looking at observations, because you just haven't observed the 100, 200, 500-year flood so often, and we again need to use some sort of a modeling tool. Here, again, we want to answer the question of when do increases in extreme precipitation translate to increases in flooding? And this time we want to look into the future. And to do that, we use a slightly different modeling chain as before, and the type of model that Clara Deser has also been talking about extensively last week. So we use a single model initialized condition large ensemble to again increase the sample size of flood events in a current and future climate. This time, it is a little bit similar to the idea of the re-ensemble pooling, but still slightly different. This time, we are using a global climate model, which is fed by one single greenhouse gas emission scenario, but also 50 different initial conditions. So we again add some perturbations to just slightly change initial conditions to increase our sample size by a factor of 50. Since I'm here interested in studying floods over Central Europe, which has pretty complex topography, I also want to make sure that I can slightly increase the spatial resolution of our climate simulations. And this is done by using a regional climate model, which was provided through the CliMax project, which was run at the Ludwig Maximilians University in Bavaria a while ago. This regional climate model ensemble is then fed into the hydrological model PRSim, which simulates 50 different realizations of future stream flow for the period 1960 to 2100. And if we look at time windows of 40 years, we get 50 model members times 40 years. That makes 2000 years of data, which we can study to look at the relationship between precipitation increases and flood increases. Now, the statistical analysis consists of identifying peak over threshold precipitation events, which we pair with the corresponding stream flow. So we want to have direct correspondence between precipitation and stream flow. And for each of these event sets, we perform a frequency analysis, again, by fitting a distribution. And we're determining different precipitation and flow quantiles corresponding to different return periods, ranging from moderate return periods of 10 to 20 years to very extreme events represented by return periods of 100 and 200 years. We then also do a dependence analysis, but this is something I won't go into detail today. And then we did a change assessment that compares precipitation and flood quantiles for the future period to those in a historic period. And the historic period here refers to the period 1961 to 2000, while the future periods refers to the period 2060 to 2099 at the end of this century. And then last, I want to also try to explain the changes we see and the relationship we observe between precipitation increases and flooding. So what we find when we look at future changes in the frequency of precipitation and discharge is shown on this figure. So we see on the x-axis return periods starting from 100 years representing moderately extreme events, ranging to the 200-yearly event, which represents very extreme precipitation events and floods that are very rare in observational records. When we look at precipitation, we see that the frequency of extreme precipitation is increasing independent of the return period, but this change becomes stronger as we increase the return period, and the very extreme events of a 200-year period, they're becoming twice as frequent as under current climate conditions. When we turn our attention to discharge, we still see this increase of the strength of the change with the return period, but we see that for the not so extreme return period, we actually see hardly any change in flow or even decreases in some cases, pointing us towards the fact that actually there's not such a direct relationship between these increases in precipitation and the changes in flooding. When we also look at magnitude changes in addition to frequency changes, we see very similar patterns. We see stronger changes for precipitation than for stream flow. We see stronger changes for the very extreme floods than for the not so extreme events. And we see negative changes, so decreases in flooding for the moderately extreme events and increases in flooding for the very extreme events. What we conclude from this figure is that there's some sort of a threshold above which the increases in precipitation are actually translated to increases in flooding, and below which these increases are not really resulting in increases because other processes at the land surface are at play. For example, soil drying, increases in evapotranspiration, or decreases in snowmelt contributions. Now, this threshold varies a bit depending on the catchment. In some catchments, we observe this threshold already at 20 years return periods. In others, it takes a bit longer for the threshold to come into effect. The threshold also varies depending on the season. It's usually a bit lower in the summer season than in the winter season, and this is observed independent of whether we're talking about precipitation or discharge. Then this threshold also depends on the elevation of the catchment. It emerges much later for the low elevation catchments than for the high elevation catchments. And last, it also varies depending on the type of flood event we are observing, on whether we observe a snowmelt flood or a rainfall influenced flood. And depending on that type, we see thresholds emerge at not so extreme events or only for the very extreme events. So this relationship between increases in precipitation and flooding actually varies depending on season, elevation, and event type. Now, what actually now drives the changes in moderate versus very extreme floods? And with moderate floods, I mean floods around return periods of 10 to 20 year return periods, and extreme floods are more those that refer to a 100-year return period. So we're here looking at the relationship between future changes in precipitation, temperature, snow water equivalent, and soil moisture in relationship to these magnitudes of the moderate floods. And we see that the flood magnitude of moderate floods is positively related to precipitation, while it's negatively related to changes in temperature, snow water equivalent, and soil moisture. When we turn to the very extreme events, this relationship between changes in precipitation and changes in flooding become stronger. So precipitation becomes more important as a driver, while the colors for the land surface processes become a bit weaker, indicating that these land surface processes become a bit less important as a driver of floods when we move to these very rare, extreme, and exceptional floods. In this talk, I tried to show you how you can get from a small observed sample to a larger sample that allows you to study the behavior of the upper tail of your flood frequency distribution, and that allows you to study the frequency of magnitude of floods with return periods exceeding 100 years. We've, in a first part of my talk, seen that we can use stochastic simulation approaches to increase the sample size and to study regional floods. And we've used this approach to come to the conclusion that regional floods are most likely in the western and northeastern United States, and also that these regional flood probabilities vary by season and in space. We've then used the approach of Reforecast ensemble pooling to study the flood magnitudes over Europe, and we've seen that these magnitudes are highest in steep and high latitude catchments. And last, we've used a single model initialized condition large ensemble to study the relationship between increases in precipitation and increases in flooding. And we've seen that there's a threshold above which extreme precipitation increases outweigh the negative effects of soil drying. Now, what does this mean for you? And could these approaches actually also become important or useful in some of your projects? I think they can, because these approaches are rather versatile. And I want to just quickly discuss here how you could apply these methods in other contexts and other regions. So for the stochastic simulation, there's a R package that provides this PRSim stochastic simulation models, which you can use in other regions. You can use it to generate stochastic series of other variables, such as temperature or precipitation. You could also use it at other temporal resolutions than daily, for example, to simulate hourly streamflow time series. And you could use it to generate multiple variables synchronously at multiple locations in space. For example, if you wanted to use the model as a stochastic weather generator. The Reforecast pooling could also be applied at other scales, for example, the global scale. There you would have to move from the European flood awareness system to the global flood awareness system, GLOFAS. They provide similar ensembles, but just at a different spatial resolution and over a global domain. And then you could also use this idea to look at other types of extremes, precipitation extremes, wind extremes, and evapotranspiration extremes. There you would just have to process different types of variables. And then last, the single model initialized condition large ensembles. They're maybe not as easy to transfer to other regions, because in order to do that transfer, you would have to feed a hydrological model, which you first have to set up or reuse ideally with these large climate ensembles, which you can get for different regions, also in a downscaled manner, but there's currently at a regional resolution not so many of them, and you would have to do some initial effort in setting up that models chain for the region you're interested in. I hope that in this talk I could show you a few possibilities of how you can shed light on these rare exceptional floods that are very rare in observations, that still allow you to tell people something about the frequency of and magnitude of very extreme and exceptional flood events. With that, I would like to close, and I'm very happy to take your questions now.